Hi, everyone. Thank you for coming out to this somewhat unusually timed theory seminar and for correctly finding your way to this room and not the room upstairs. I'm very excited to have Zihan here today. He's currently a postdoc at Rutgers/Dymax, which for those of you who don't know is kind of like a discrete something math institute.
This is discrete. This is mathematics and computer science.
Yeah, there you go. Okay, so discrete mathematics and computer science. Zihan did his PhD at the University of Chicago, where he was advised by Julian Chuzoy, and also Latsiva by
Co-advised. Yes.
Co-advised, yes. Okay. And he's done a lot of like really nice work in like graph sparsification and sort of related areas, some of which I guess he'll tell us about today. So.
Okay, thank you, Alice, for the introduction. Yeah, I'm very happy to be here. This is my second time here. This is sort of the fortunate place where last time I visited here won a championship. So I would like to, very happy to be here again. I hope that I can be here later. I get an interview or something.
Oh yeah, he's on the job market also.
Yeah. So the topic I'm going to talk about is on 1+ϵ approximate flow sparsifier. It's a recent work by me and my collaborator Yu Chen with a postdoc from EPFL. Okay, so this paper has just been accepted to SODA. So some of you go to SODA. I'll present it again in 3 months. So the title contains the word sparsifier, and this work falls under the umbrella of graph sparsification. And the motivation is we are having larger and larger graphs by the day, and we have to process them many times, frequently, every day. So there are 3 approaches in processing this theory, from what I understand. First one is just to design faster algorithms. And the holy grail, to my understanding, is to design an algorithm that runs in this time, which is called almost linear sometimes. M times m to the 1+1. This m to the little 1 is what almost means. So it's m polylog n, this is called linear, and near linear. And this is called almost linear. Okay, so some success have been achieved in this direction. For example, the famous Max Flow paper last year, it's the best paper of Box 22, as some of you should know. And also very recently, the op-pair version of Max Flow can also be done in almost linear time. Okay. And this is flow cut. The distance, single source shortest path, we know it can be done by a single BFS throughout the graph. So nearly number of edges I want to stand out. But the op-pair version of that, at least people do not believe they can be done in almost linear time. Some researchers believe there are conjectures saying that we cannot do it in subcubic time. Subcubic means something less than n to the 3. So we can just, the best thing to do is just to perform DSF from every products. So this is the first approach, just to design faster algorithm. And some problems, we believe we cannot do it in almost linear time. The second approach is to perform this graph computations in different computational modes, more than once. The motivation is we have more and more computers, more and more powerful computing machines. But why don't we assign different parts of the graph to different computers and let them perform computation on their assigned parts while talking to each other? And this is exactly what we are doing in the distributed and parallel models. Okay, and there are some other models like dynamic streaming, all very interesting. For example, if we view the graph as being given to us as a stream of edges and vertices on the fly, we see them one by one. When we have unbounded response time, but bounded space, we're in the streaming case. When we have unbounded streets, the space, but bounded response time, we're in the dynamic setting. So they're all very interesting models, and there are many interesting results obtained in this model in the past decades. Okay, so there's a third model, third approach, at least the approach that I like most, is called compression. So the motivation is, although the input graph is very large, the number of vertices of interest to you could be very few. For example, if you live in Providence, then you probably only care about where you live, where this building is, where the gym is, where some restaurants are, okay, and the airport, train station, a total of 10 locations out of 1 million nodes in the network. So why do you need to perform the graph computation on the whole graph if you only care about 10 locations? This is exactly where the compression is going to help us. It takes the large graph as an input together with a few vertices of your interest called terminals, marked in red, and compute a small graph containing those terminals while preserving the important information about them. Graph need to be smaller, significantly smaller. Okay. And now you can run whatever the algorithm you like on this small graph. It will be very efficient. Okay, so here we consider n squared, n cubed as inefficient, but here n fourth, n to the 10th will be all very efficient, as n itself is already very small. Okay, so that's what graph compression does. So ideally, we want the graph to be as small as possible and the information to be preserved as accurate as possible. And it's the trade-off that we are going to study. So what are the most important informations? Cut, flow, distance. And today we're going to see one of them, which is flow sparsifier. Okay, so cut and flow sparsifier are highly correlated with each other, and they are usually defined together. So let me first define cut sparsifier for you. Oh, by the way, how many of you attend the frontier class this semester? I suppose some topics should
1, 2, 3.
Okay. Yeah, that might make this topic easier to understand. So usually I spend 3 to 5 minutes explaining just the definitions. Okay, so but yeah, I'll introduce it anyways. Okay, but it's good to know that some of you are already sort of familiar with these functions. So cut sparsifier. So for a large graph with respect to a set of terminals, a cut sparsifier is a small graph containing those terminals, such that for any partitioning of the terminals into two sets, it's 3 against 4. The mean cut separating them in the original graph is about the same as the mean cut separating them in the sparsifier. We call this graph the sparsifier. Okay, the definition here, mean cut is about the same. Okay, so about the same, I mean within the factor q. Ideally, q is 1, like all the mean cut are preserved exactly, but we allow some small factors, for example, constant or slowly growing function of the number of terms. Okay, so flow sparsifier is, the definition is a little bit more complicated, but it's generalizing the cut sparsifier in the natural way. Just think about it for 3 minutes. Okay, so what is the definition? It says for any demand on the set of terminals, the mean congestion of routing that demand in the original graph is about the same as the mean congestion of routing that demand in the sparsifier. Okay, it's still about the same condition. But what exactly what I'm talking about? What is a demand? The demand is basically I want to route 1 unit from here to here, 2 from here to here, 3 to 4. It's just assigning a number to a pair of terminals. A flow for routing that demand is just a flow that really sends 1 unit from here to here, 2, 3, 4. It's really such a flow realizing this demand.
So a single commodity?
Multi-commodity.
Multi-commodity.
Yeah. So I want to send 1 from here to here, 2. All simultaneously. Yeah, so the congestion of routing that demand in the graph, or congestion of the flow of routing that demand, is basically how much I have to inflate the edge capacity in order to accommodate such a flow. Okay. So I want to route 1 from here to here. If all the edge have capacity 0.1, then I have to inflate them 10 times in order to accommodate such a flow for really sending 1 unit flow from here to here. That makes sense? So yeah, so it can be large. So the larger the capacities are, the smaller the congestion are. So the 0.1 requires you to inflate 10 times. But if the capacity is 10, the congestion is 0.1. So the larger capacity is, the smaller the congestion are. So it's really measuring how well you can route this demand, measuring the ability of routing this demand. So it can be large or small, but we want it to be preserved between the original graph and our sparsifier. Okay, so that's what flow sparsifier is. Hope this makes sense. Even you have already maybe seen something before. The research focus is, as I described, the trade-off between the quality and the size here. The size is just how many vertices are there in this graph. As for now, just measure the size by the number of vertices. Okay, so ideally we want Q to be as small as possible and the size to be as small as possible. And this is the research focus of our problem. And yeah, is the definition clear? Okay, so let's see what are known in this trade-off. So actually, I would say only 2 extreme cases were studied in this problem. The first extreme case is the horizontal one. The one is the leftmost vertical one. It's 2 extreme. So in this extreme, we only allow terminals in the sparsifier. Okay, so we want to construct a small graph, but we only allow terminals in it, no other vertices. You can build whatever edge you want. In this case, what is the best quality you can achieve? So this was first initiated by Uncle Moitra and followed up by a sequence of other papers. Altogether, they show that the best quality achievable by both cut and flow sparsifiers is something between log t over log t and square root of log t. There's still a gap here. People have been trying to close it, but not there yet. Okay, t is the number of terminals. And for everything in this picture, the yellow one refers to cut results, purple one refers to flow results. Okay, so the main message is we cannot get a constant here. That's a super constant. The other extreme setting is the exact preserving setting, where we require the quality to be 1. So for any mean cut, the values here is exactly the values there. Okay, quality 1, you still recall exactly matching. Okay, and this is the case where cut and flow sparsifier results are separated. For cut sparsifier, we can show that there exists always a cut sparsifier of size no more than 2 to the 2 to the t, and it's lower bounded by 2 to the t. So there's still a super exponential, like an exponential gap here. Okay, and the flow sparsifier, a very recent result by Cross-Gamer and Mosenson showed that even for 6-terminal network, a flow sparsifier may require infinite size. Okay, so what does infinite mean? Infinite means there's no infinite with respect to the number of terminals. So there's no function that depends only on the number of terminals that can serve as the exact flow sparsifier size output. Your size have to be depending on the number of vertices in the river graph. So no function only depending on t. It has to depend on n in some way, like log n, polylog n times t. That's possible, but not only depend on t. Okay, so that's
in the lower corner case. Did I understand correctly that you're allowed to introduce new edges?
you can build whatever edge you want.
And you can give it whatever capacity.
Yes, that's right.
I see. But this, so then, kind of what's stopping you from making the graph complete and giving every edge infinite capacity and then
So
assessing?
we want the congestion to be both upper bounded and lower bounded.
I see.
So it can increase the capacity, but not too far. I mean, that's also not
Okay,
preserving it.
Sorry. So what's preventing you from just computing a Gormley tree and compressing? Sorry,
That's a
I'm
good
just
point.
confused. Yeah.
Yeah, that preserve ST flows, not multi-commodity flows.
Oh, okay. Okay, cool.
So when you try to do cut specifier, you just optimize for cut.
Yes.
And then when you do flow, you just optimize for flow.
Yeah.
But they are like very closely related notions, right?
Yeah.
Like,
So
for example, in these constructions, where
how similar are they?
Yeah.
Yes. So they are similar, but sort of not one implying the other. By definition, flow sparsifiers are automatically cut sparsifiers, but not the other way around. This is the relation between the two definitions. The condition, they are sort of similar, but they are doing different things, kind of solving slightly different linear programming rounding them. But the methods is very same. It's only the programming they are looking at are slightly different. That's probably the thing I can say.
Or I guess I'm curious, like whether you can achieve both at the same time.
Achieving flow automatically can be cut.
I see. Oh, okay.
Sorry. So, sorry. I just want to follow up on my question. But so I understand the flow part, right? Where preserving cuts may not preserve for multi-commodity flows.
Yes.
But you have this cut result, right? Which only cares about the size of the cut. So why doesn't Gormley tree work again? Sorry.
So cut flow, they are the same for ST.
Right.
ST cut equals ST flow.
No, but you're only preserving cuts.
Yeah, but I'm
What?
preserving okay. So it's for any partition of the graph into two
Oh,
sets.
sorry. So you're saying Gormley tree only preserves ST cuts,
That's right.
but you're preserving any subset
Any
of terminal.
partition.
Right. Okay. Yeah. Sorry. Thank you.
Another
I
question.
think I figured out the answer to my question.
Okay.
I'll just keep it.
Okay, so these are the previous results. Basically, only two extreme cases are studied, and this is wide open between them. So our results can be viewed as trying to step in this area for the first time a little bit. What we prove is that when we allow 1+ϵ inequality, we can also push the lower bound to infinite. Okay, so in other words, there's no function depending only on t and epsilon that can serve as the upper bound of the sets. Okay. So Yeah, there's a star here. I will go to that immediately later. But I'd like to first make two remarks about this result. Okay, so first, it's completely different from the proof of the exact case. As the exact case, they consider all routable demands and formulate it in a polytop. Okay. And they say that in order to characterize this polytop, you have to achieve very large slope. And I can construct a graph exceeding that bound, etc. So basically, they argue about polytop. But when we allow 1 plus epsilon perturbation, polytop can be changed significantly. Like some positive slope can be changed to negative slope. So it's sort of hard to adapt their proof to ours. First point I want to make, significant difference. The second is, this is actually answering a question raised in some previous work. So in the previous work by Antonio Gupta and Cross-Gamer, they construct a data structure trying to preserve all 1 plus epsilon max flows with multi-commodity flows. And they established a framework in this direction. What our result says is that unfortunately, their framework does not give us what they wanted at the beginning. Okay, so that's the two remarks I'm going to make. So I would like to get to that star right now. So we haven't really proved the result I claim right now. Okay, so what is the normal way of constructing a flow sparsifier? It is by looking at the graph, partition the graph into clusters, and contracting each cluster into a supernode, and be done with it. This is the way of constructing a flow sparsifier. Okay, so it's quite intuitive, quite conceptually simple. Okay, so there's an additional advantage of this approach. It's basically for constructing a flow sparsifier, we want the congestion to be upper bounded by something and lower bounded by something. It's measuring the ability of routing some demands. So we cannot increase too much or decrease too much. And what this contraction is doing is essentially adding infinite capacity edges between the vertices you are contracting. So it's essentially only increasing the capacity of a lot of edges without decreasing anything. Okay, so it's only increasing the ability of routing the demands, and therefore it's only decreasing the congestion. And you need to just bound how much it can decrease. So it's like two directions you want to prove, and the contraction-based approach gives you one direction of method. That's why all the algorithmic results so far that I know of adopted this approach. Okay. So our results is actually saying that the contraction-based flow sparsifier, we cannot get 1 plus epsilon in finite size. So there are two results. For every 5-terminal network, okay, there is a quality 1 plus epsilon flow sparsifier with size depending only on epsilon. It depends on both 5 and epsilon, but 5 is constant, so it's okay. But there exists 6-terminal network such that no matter what bound you give me, it can construct to you a graph such that any sparsifier not exceeding this bound, the quality has to be bounded away from 1, not 1 plus epsilon. This omega 1 is some absolute constant, which is 10 to the 18. We haven't tried to improve this very hard, but it can be probably brought to 10 to the minus 3, like that. But it's an absolute constant. Okay. So another way to interpret the theorem 2 is just a 1 plus epsilon. It's infinite. It's impossible. Require infinite size. Okay, that's all the main results.
What is the uppercase n in size n contraction-based flow?
What is the uppercase?
No, what is n the number of
Oh.
vertices overall, or the number of
This is-
vertices in a cluster, or?
Yeah, this is for any size bound you want to give me. I'm telling you this by size bound is impossible.
Oh, okay, gotcha.
So intuitively, just say 1 plus epsilon require infinite bound. Are those main results here? Yeah. Okay, so from now on, I'm diving into how to prove these results. Although there are like 2 theorems, but there's just one chain to follow. At the end, it will break into 2 results, and you'll see the difference between 5 and 6. So it's really one line to follow. Yeah.
Maybe I'm jumping the gun, but are there results known for non-contraction based?
So yeah, the previous result for this is non-contraction based for this is for any
Okay, but for 1 plus epsilon.
yeah, no. So actually,
Okay.
all the algorithmic results, there are some other special case like other dots I am not showing in this picture, all adopted contraction based approach. So I think there are some sampling based. One very special case in their paper, dealing with some quasi-bipartite graph, only that. Sampling based, that's a solid contraction. No other than I know of. Okay. So I'll start by describing the approach of proving those two theorems. Okay. So let's look at what is the congestion of routing of demand. It can be actually computed by a linear program. Okay, so recall that congestion is the amount we have to inflate our edge capacity in order to accommodate such a flow. In other words, it's how much you have to inflate in order for this flow to be routable. Or if you do not inflate anything, how much or what fraction of the current demand you can route. So it is the lambda is what lambda means here, the fraction of the current demand that you can route without inflating anything. So we are minimizing 1 over lambda, equivalent as maximizing lambda. Okay, so this is like routing lambda fraction of the demand, and this is not violating any capacity constraint, so they are all linear. It can be computed by a linear constraint. Now we can take a look at this due. So I'm not showing you the process of taking the due as standard. Okay, so
sorry.
Yeah.
I know the answer, but I'm asking the audience.
Okay.
So the PTT prime there is the set of all passes.
Yeah. So for any pair of terminals, like summing over all passes connecting this pair of terminals. Yeah, I will need to go into more details in the due, by the way.
Right.
Just one second. Yeah, explain this more. So ideally, intuitively, the primal is maximizing the L infinity normal sum factor, and the due is minimizing the L1 normal sum factor. Okay. So, and this is how it looks like. So minimizing the L1, that's L1 factor. So, and what we're going to do is taking the due, solve the due, and turn it into a contraction-based flow sparsifier. This is the approach. Okay, let's look at the due in more details. So first, we can first ignore this capacity. Okay. Let's just assume that all capacity sets is 1. As even if the capacities are real values, we can think of them as parallel edges. It doesn't change anything. Okay. So this makes it simpler. Okay. Now, what are the variables? There are two types of variables, LEs and delta TT primes. L gives a value to every edge that can be viewed as the length of this edge. Okay. So normally when primal has a flow congestion meaning, due have length distance meaning. Okay. So if you get familiar with that, taking some dues, you will see normally lengths are assigned to this. Okay, but what about delta values? The only connection between the L's and deltas is this constraint. It says for any pair of terminal and for any path connecting this pair of terminal, the total length of all edges in this path is at least the delta value between them. So now another way to say it is that the delta value is the shortest path distance connecting these two vertices when the graph has edge-weighted LEs. Okay, so all these three lines are saying LEs are distances and delta E's are, LEs are lengths and delta E's are distances. Okay, and we can ignore all of those right now. And there's another one, the first one, which is a little hard to understand, but let's think that it's saying some average distance is larger than something. Okay, it's just something has to be lower bounded by something. Okay, let's, for now, just think of it like this. Okay. We will like we do not need to actually dive into that. We will eventually preserve something stronger here. Okay. That's for now, think it's just saying this. Okay, so what we're going to do is solve this problem, to solve this LP, get a solution which consists of a lot of edge lengths and distances used by them. Okay. And from them, construct a contraction-based flow sparsifier. Okay, so what should we do to get a flow sparsifier? Contraction-based. Okay, so what is a contraction-based flow sparsifier? It's basically a partitioning and contracting each cluster into a superdomain. So what should we do to this length and distance values to make it look like that the clusters are being contracted? It is to give non-zero lengths to edges you are not contracting, but zero lengths to edges you are contracting. Okay. So we can manipulate edge lengths. This is just another way of rounding this LP. To get a solution, we manipulate to another solution to make it look like it's coming from a contraction-based flow sparsifier. Okay. What we will do is just manipulate lengths. So we will compute a partition in the size S and reset edge weights such that edge within parts now have zero length, and edge between parts have non-zero lengths. And we still want it to be a feasible solution of this dual LP in order for it to be really preserving the congestion. Okay, so the first condition still needs to hold. So the average distance is still larger than that thing. This is still hard to master, but let's try to preserve something stronger. Let's try to ensure that after manipulating the edge lenses, the distance between every pair of terminals do not decrease. The claim is that is enough for guaranteeing this constraint to hold still. Okay, so originally this holds, and this is constant. I'm not decreasing any single value of this. So this continues to hold. Okay, this is something simpler to remember. It's indeed something stronger, but let's just ignore the original case. And we still do not want the objective value to be blown up by too much of a factor, because this is directly just 1/λ. It's a conjecture. So how much it blow up here, it directly reflects in our quality. And we want 1+ of quality, 1+ of quality, or Q quality here. Okay, this I suppose is already a lot to remember. What does this mean? What we want to do, and this is only for routing one demand. Eventually, we want to preserve all demands, flow specifier for all demands that is equal. Okay, but let me try to ease your mind with the following previous work mentioned previously by Antoni Gupta and Koskaber. They say that we only need to deal with one demand. Okay, so they say that if we can deal with one demand well, then you can simultaneously deal with all demands well. Specifically, if size P here can be achieved with quality Q here, then you can achieve quality Q times 1+ epsilon simultaneously for all demands with size bounded by some function on P, T, and epsilon. Okay, this is some horrible looking function like super exponential maybe W. Okay, but it only depends on P, T, and epsilon. So if P only depends on T and epsilon, then this function only depends on T and epsilon, and is finite in our sense. And all we need is finite. Okay. So we only need to deal with this problem with P depending only on T and epsilon. Okay. Okay. So really from now on, we just look at this problem. Ignore the requirement of routing all demands. We just look at routing one demand. Okay. Yeah.
How does this reduction work? It's just like multiplicative weights or something?
Discretize the space of demands a little bit. Like for any coordinate, for any pair, you give 1+, 1+ epsilon, 1+ epsilon square, etc. That give you a finite number of demands. And they said that you need to only preserve demands. That's at the cost of losing a 1+ epsilon here. The number of demands you need to preserve also depends on us. So we only need to deal with one demand from now on. Okay. So what we want to do, get a lot of edge lenses together with their induced distances, manipulate edge lenses such that the distance between any pair of terminals do not decrease. And the total length, okay, this is the objective, total length do not increase too much. Okay. So a special case of this problem was actually studied. It's called zero extension problem. This is this topic has also been covered in the class.
You presented it in
okay, great. So that's exactly the same problem with the special case where we only allow T parts. Okay, so here we allow P parts. P can be any function depending on T and so. So if we only allow T parts, one part containing a terminal, then it's the zero extension problem. And that has been studied in the past. Actually, all these previous results on the special case, on the bottom line, if you still remember, is obtained by studying this case, obtained by studying the problem. Actually, the LP, intervening gap of this LP. Okay, and what we are really looking at is a standard node version of that problem called zero extension with standard node. Okay, so we allow a partition into more parts with P depending only on T and epsilon. Okay, we allow manipulating the edge lenses and the distances used by it, such that we are minimizing this ratio. Okay, so why this ratio? It's just requiring that the objective do not blow up by a lot. We have an objective, and we manipulate, get another objective, to making sure it's not blowing up by a lot, basically making sure this ratio is on it. And the quality is just how small can we push this ratio be in this case. Okay. And here, as we're looking at the quality 1+ epsilon case, And by the reduction, we lose the 1+ epsilon there. So we're really looking at the quality 1 case. So the total new edge length is no more than the total old edge length. This is what we really want to achieve. Okay, so
Sorry.
yeah.
Can you explain this ratio a little bit?
So okay, so what
and
is
how it relates to
okay. So what is the objective? It is the total edge length. Okay. So the ratio is just the total new edge length over total old edge length. This is the ratio. Okay. When we only allow terminal parts, like each edge is contracted to a terminal edge, the distance is the new edge length. And this is the total new edge length. This is the total old edge length. That's the ratio. It's not essentially saying anything tricky. Maybe just want to look at this ratio. It's the same thing, but this is the total new edge length. This is the total old edge length. That makes sense.
Yes, but is it clear that so you have a dual solution, right? You're
Yeah.
setting all the
We're
so
constructing.
you want to find a partition,
Yes.
right? And after you find that partition, you set all the internal edges
To
to
zero.
have length 0.
Yeah.
And but you don't change.
And manipulate all edges, just setting them artificially to 0, but increasing others, such
Okay,
that
so you're increasing. Okay, so for a cross cluster edge,
Yeah.
you're increasing it to.
something. I mean, in this case, we have to increase it to the distance between the two corresponding terminals.
So basically, if I have two clusters, S and T, then every edge between S and T will be increased to the maximum distance between any pair of nodes in S and T.
Just a pair of terminal distances, just the terminal distances. You will see an example later on, maybe in a
Okay,
slide or two.
that's fine.
Yeah.
Yeah. All right.
Yeah, it's good trying to understand this, but yeah, you'll see examples. But it's, yeah,
Sorry, and just to be clear, when you're working with Steiner nodes, the only constraints you have on the distances in the resulting graph are still between terminals. Like
Yes.
you don't go, yeah.
yes.
Okay.
So think of them, you have pinned some points on the plane, and it's like strings representing those edges. We're contracting them, and all the remaining edges are strings constraining them. But the only constraint are really between pinpoints. That makes sense. The junctions between strings are flexible. The only constraints are between pinpoints. Yeah. Okay. So from now on, we will only look at this problem, and this is the only goal we want to achieve. If we can achieve this throughout all the reductions up to the front, we'll get 1+ epsilon flow Sparsifier with finite size. Okay, so this is the problem. Give you a graph with edge weighted and a set of terminals. You want to partition the graph into p parts, manipulate the edge lengths such that the terminal distance do not decrease and the total edge length do not increase. Okay. So we can forget about everything before this slide now. Let's look at this problem.
So is there some bound on the number of Steiner nodes you're allowed as a function of T?
Yeah, a function of t.
Okay.
Yeah. That's right. Can be any function. So
Any bounded function.
any function.
Okay.
Okay, let's just start look at special cases where we better explain what it's really doing. Okay, so let's have special case where there are just two terminals. What we want is find a partition, contraction, manipulate the edge lengths. What we should do in this case is just find a mean cut. Okay, contracting whatever lies on the left to T1, contracting whatever lies on the right to T2, and get a graph like this with many parallel edges in between. How many parallel edges? Mean cut many. So basically, we discard self loops and retaining parallel edges. Okay, so after this operation, this is the graph we get. And we also, we also need to assign lengths to each of these edges. What should we assign? It should be the distance between them in the original graph, as we do not want to decrease the terminal distance. So they have to be at least this much.
But yeah, sorry, why does it have to be a min cut? Can they just take any?
Yeah, I mean, this is just a solution. You will see
Oh,
another
okay.
example here. Exactly. There can be more flexible in the next slides we're going to show. This is just be familiar with this problem a little.
Okay. And well, my second question though, I guess like if you're assigning every parallel, it's not clear to me that if you assign every parallel edge, the like distance between the two terminals, that you actually don't increase the total.
Yes.
Line.
Okay. This is the point I'm getting to. Right now.
Okay. I'll shut
So
up.
how should we prove this is a good solution? We just need to prove that in the original graph, the total edge length is at least this much. Why is that? It can be a homework problem.
Oh, okay. No, I see. Sorry. Yeah, I was just.
Okay. So just by max flow mean cut theorem, if the mean cut is Z, then there exists C edge disjoint paths in the original graph connecting T1 and T2. They use disjoint set of edges. Each path has to carry total length, at least distance between T1 and T2. And they are disjoint, so the total is nothing tricky is happening here. Max flow mean cut. Okay, is that good enough for this special case? Okay. Another way to look at it is just we need only two parts in dealing with two terminal cases. Okay, just left to right, just two parts, P equals 2. So let's be more flexible in this very special case. We want to generalize later. So let's look at a special case where all the other vertices lies on the shortest path of a T1, T2 shortest path. Let's think of the graph as given to us like this. There can be other edges connecting different pair of vertices in between. In this case, we can definitely just do a mean cut as before, whatever left on the right, whatever right to T2, and get the same approach. But we can be more flexible here. Let's do this. Pick a random edge on this path with probability proportional to this length, and perform a random threshold cut. Okay, so this edge is chosen uniform at random according to its length, and the threshold cut is like whatever lies on the left of this threshold is contracted to T1. Whatever lies on the right of this threshold contracted to T2. Okay. So in this case, we still want to prove that there's a good solution. So the total new edge length is bounded by the total old edge length. So for each single edge, it is either split in the sense that two endpoints are contracting to different places. In that case, it will be given the distance T1 and T2 as its new weight. Or it's not split, meaning it's both contracted to the left or both contracted to the right. It will have 0 length as its new weight. So what's the probability of it being split? It's the probability that one of these edges was selected. It is the total length on this path between these two endpoints. This is the distance on path over the total distance of the whole path. This is the probability. And when it's being, I think it's missing this times. Okay, so close to get it. Okay, so the distance on the path is bounded by the edge length. This is because this is the shortest path. So any path has to be longer than that. Otherwise, it's not shortest path. So this two cancels out, and it is really saying that the expectation of the new length is bounded by the expectation, bounded by the old length. Okay, so it looks like it's really nothing tricky here. It's just it's a line metric. It's a path metric. Sometimes people give name to this property when you perform a random cut and contract. New edge length, the expectation is bounded by the old edge length. Sometimes people call it decomposing or separable. So nothing is tricky is happening here. It's basically L1 is decomposable or line metric is separable. Okay. Okay. This example will serve as an important subroutine as we understand t equals 3, 4, 5 case. Eventually, you will see the difference between 5 and 6. Okay, that's going to be the plan for the next 15 minutes. Okay. Okay, so starting t equals 3 case, things start to become a little bit interesting. Okay, let's look at this graph. So first observation, so A, B, C are terminals, P, Q are not terminals. The first observation, all the shortest passes are supported by P. Okay, so AC is this shortest pass, and AB is this shortest pass, and the BC is this shortest pass. Okay, all are supported by P. So recall what we're going to do. We are going to manipulate edge lengths so that the total edge length decrease, but terminal edge do not. So total edge length do not increase, and terminal distance do not decrease. So we might not want to touch P. This is because if we decrease this by delta, we have to increase this by delta and this by delta in order to preserve AB and AC distances. Okay. That is like this decreasing 1 delta and increasing 2 delta. That's increasing the total edge length, which we do not want to do. So we do not want to do anything to P. Just keep these 3 edges there. But we can definitely do a lot of things to Q, as we can decrease this 4 to 3, decrease this 6 to 5. Now Q starts to support shortest passes. Right? This AQB is another length 7 pass between A and B. So it's not again the shortest. And BC is also the shortest between B and C. It's 5, 3, 3, 5. They're both 8 in total length. Okay. And we cannot decrease further. So this is just something we should do as a very first step, a simplification without changing anything, without decreasing any distance between terminals, just decreasing the edge length by the.
Oh, no,
Okay.
yeah.
If you look at it closer, you will see that the Q here can be actually identified with the point on the PB segment that is at distance 2 to P and at distance 3 to Q. So if you look at the distance, 4, this is 4, 3, this is 3, and 5, and this is 5. Q is actually there. So, but if we are in this 3-segment case, we know how to deal with it. Just treat it as 3 segments separate. A random cut here, a random cut here, a random cut here, like in the 2-terminal cases. This is how we deal with 3-terminal cases. Actually, this holds for, this is not an exception. We can prove that for any given 3-terminal graph, we can construct a skeleton like this, where these 3 are just line segments whose length only depending on the terminal distances. Okay, so this is AB plus AC minus BC. You can check this actually preserve the terminal distance, as this plus this is like AB and BC cancels out. It's only AC left. So it's the distance between A and C. This skeleton preserves the terminal distances, and what's more, we can project all the vertices into the graph to some point in the skeleton without increasing the edge length of any single edge. This is what we can do. We can prove. Okay, and what's left? We just random cut, and sort of reduce it to the two. Okay, so it is this structure and this projection that is really the crucial subroutine of the algorithm, which I'm going to go into detail for the. This is the last technical part.
Sort of out of left field question. If instead of measuring the complexity by the number of terminals, you had a topological measure, you consider a topological measure and instead look at graphs that are planar. Does this cut approach work for any planar graph, regardless of how many terminals there are?
So yeah, I included some of the results in the slides in some of my previous talks. So planars are much simpler. Okay, so let me give you what planar graph we can do in planar graphs. 1 plus epsilon quality, near linear size. And the Sparsifier is also planar. This is what we can do. So it's sort of a completely different world from this. Very simple. And the approaches are not considering this metric-based thing. It's just by looking at a planar, fully utilize the planarity.
Right.
Cutting the graph into 2 pieces recursive. Yeah, that's a different story. So,
Okay, sorry.
yeah, no problem. It's just much simpler than this, I would say. Okay, back to this. Yeah.
If I I'm trying to think about like how to actually construct the skeleton. Like if you just think of the 3 shortest paths between each of the pairs,
yeah,
can you then just sort of like you may sort of end up like with this triangle
yeah,
of their intersection?
getting to that.
Okay.
In the next slide. Yeah, you are sort of always one slide ahead of me. Okay, so this structure actually has a name. We thought we discovered that, but later on we look at that 30 years ago. There's some math community paper. They have this coin already. It's called tight span. It's sort of really like things need to be get tight. Okay, that's the name. So what we are doing is take the input graph with weight, project all vertices onto the tight span, and cut the tight span. That's what we are doing here. And getting into the definition of tight span. Let's look at what this structure is. Okay, what is a tight span? This is the last notion. And if you want to take anything away, maybe it's the tight span. Okay, so tight span is whatever we have after doing this first simplification step. So what we want to do is just decreasing the distance from a center point to the terminals until we cannot do so anymore. This is what we get. It's vertex in the tight span. Okay, a tight span is defined with respect to a metric. The metric contains k points, which are the k terminals. Okay. But I want to imagine that there are many other imaginary points lying in this metric, which are represented by k-dimensional vectors. Each such vector represents a point that is at distance x1 to terminal 1, at distance x2 to terminal 2, 3, 4, etc. Each vector represents an imaginary point in this metric. Yeah,
Just to be clear, when you say imaginary, it's not like
it's
complex numbers imaginary.
Oh, no.
Okay.
So you just imagine. Yeah.
Okay.
So we just faked points. Yeah, imaginary. So all these are real numbers. So they have to respect all the terminal metric, in the sense that if I'm at a distance x1 to terminal 1, at distance x2 to terminal 2, then these two distances, the sum of them cannot be smaller than the distance between terminal 1 and terminal 2 itself. So that's respecting metrics, the first condition. And they need to be tight. Tight means I cannot just reduce one coordinate without violating anything. So any coordinate cannot be further reduced, which means for any coordinate, there exists another coordinate, such as xi and xj are already tight. Tight means the sum of these two is already a distance between t and t2. That's the tight set. Okay. So it is the condition B that gives a tight meaning of this space. Okay, so let's see an example. Again, this is basically the last technical slide. All slides after that were pictures. So this is the 3-point metric we have seen before in the previous slide. So what is the time span of this look like? It's a 3 line segment there. Let's see how it is constructed. Okay. So the time spans are 3-dimensional vectors. Okay. So let's say what A represents. A represents the vector 0, 7, 5, because A at distance 0 to A itself, at distance 7 to B, and at distance 5 to C. So A represents 0, 7, 5. We want to see how we can move from this point. Okay, so basically we want to see how we can manipulate this 3-dimensional vector. From the second condition, some constraint has to be tight. That's the constraints that constraining us in the degree of freedom of moving this vector. Okay. There are 3 variables, 3 constraints in total. 1, 2, 2, 3, 1, 3. We have to pick 2 of them to be tight. As if we just pick one of them, then there's a coordinate hanging there. There's no constraint preventing us from further decreasing that. So we pick 2. Let's pick AB and AC. They're all symmetric. Okay. So what we can do here is increase the distance to A and decrease the distance to B and C simultaneously in order to preserve AB and AC tight. Makes sense? So we can, if we go 1, then it's 1, 6, 4. This is still tight, this is still tight. Okay. And if we go 2, we get 2, 5, 3. And then we reach the center. Or we cannot do this anymore. As decreasing 5 and 3 simultaneously further will break this inequality. So we are there. Okay, what we're doing is keep AB and AC tight and do plus minus minus. And we do the same for 2 other segments from 2 other endpoints. And we have to reach at the center point simultaneously. This is no coincidence. It's not hard to provide that. Okay. This is, I understand, not a rigorous proof, but hope I give you some intuition of how this is constructed. It's really the tight span that's now leaving us with a more degree of freedom. Okay, we'll be looking at 4 terminal tight spans, 5 and 6, and see the difference between 5 and 6 eventually. Okay, so the 4 terminal tight span, I'm not going into the detail of constructing that, but eventually we still push things away from the terminal and get that until we cannot. We do this for all the terminals, and eventually we didn't end up at the center immediately, but get a structure like this: 2 and 2, 3 and 3, and 5 as the distance between terminals. What that essentially is a 2-dimensional subspace in the tight span. So 3-point tight span is only 1-dimensional subspaces. Now we have 2. Why is that? We need some tight spans to constraining all the coordinates. All the points in this area, their tight constraints are this constraint and this constraint. That is 2 constraints covering 4 coordinates. Enough for it to be in the tight span. So we have 2 degrees of freedom left. 4-dimensional, 2 equalities. We have 2 degrees of freedom. So from here to here, it's increasing the distance from this cluster, from this terminal, and decreasing the distance to all the rest of the terminals. But if we move in this area, let's say move in this direction, it's increasing the distance to this 2 and decreasing the distance to this 2. Or we can move in this direction, that is increasing distance from this two and decreasing distance from this two. So it's a two-dimensional area. The thing is, this two-dimensional area is equipped with an L1 metric inside it. So it's 2, 3, 5. It's really showing it's an L1. And L1 we can do several. It's several. So we can do 2 random cuts to cut it into 4 points. Okay, hope you get this. And basically that's all the intuition. L1 states are separable, so 4 is okay. And how many points we need is 8, because we will do 2 random cuts to cut it into 4 areas. This area goes to this point. This area goes to this point. And definitely we want to do 4 random structural cut for tails, and eventually get 8 standard point out of that. Okay.
So is it true that if the graph that I start with is embeddable to O1, can I always
Yes.
do this?
Yeah, if that's embeddable to L1 automatically. But that's obtained from solving an LP.
Yeah, so it's not good.
You are done with this topic.
Yeah.
Okay, so that's a 4-terminal case. So now I only want to show you some pictures for 5 and 6. The good thing about 5 is, although it's more complicated, it's still at most 2-dimensional. So we need 3 constraints to cover all coordinates. So it's still at most 2-dimensional. Only it is now more entangled. It's not correlated. So in order to partition this 2-dimensional subspace, we need a cut here and a cut here. But in order to partition all of them, we need cut to be correlated. So it's like for each we need 2 cuts. For 5, we need 10 cuts, but it's really 5 cuts serving the role of 10 cuts. So this point gives this cut and this cut simultaneously. So they need to be correlated, but still L2 are separable. So there are actually 3 types of time span for 5-point metrics. This is the first type. This is the second type. There's another type which is similar to the third type. It's similar to the second type. So this has a little bit interesting shape. As one piece of paper is not enough to hold it. It's like a piece of paper with an angle standing on it. It can be flipped either downwards or upwards. If flipped downwards, it's like this. Upwards, it's like this. It's by looking at a sub-time span of a set of 4 points on it. Okay. But it's still L2. Just we need to partition it more carefully. And the 6-terminal network, the LP is, the time span is 3-dimensional. It's possible to cover this 6 coordinate with 3 constraints. So 3 degrees of freedom left, and that's making it 3-dimensional. And 3-dimensional, for example, if we look at this 5 point, the time span is like this angle. If we look at this 5, then 5 points like this. We have to contain the whole body. So it's the whole span. It's 3-dimensional, and 3-dimensional is not decomposable. Okay, I'm trying to give an intuition of why that's true. 3-dimensional is not decomposable, but 2-dimension is decomposable. Okay, so recall what we have done here is plus minus minus in order to construct that time span. That is essentially moving in some L infinity direction. L plus minus minus is just a vector with maximum values found at L1, L infinity. So the time span actually is automatically equipped with L infinity.
Yeah, I think we're losing the room.
Oh, in
Teaching in class.
right now.
Yes.
Okay. So L1 and L infinity are the same in 2 dimensions, but not the same in 3 dimensions. That's it.
Okay, thank you.